All right, let's do this. So let's get started with lecture. So today is, what's today's date? Oh yeah, March 4th, 2025. So the last two lectures I've been gone, and we've been going over convolution and then how to use convolution to solve circuits. So we went over the impulse response. In particular, when we look at, in order to kind of talk about convolution, we have to think of a function. So basically like f of x as something that we input a number and then it gives us another number out. And in particular, when we do convolutions, something's gonna happen to our input before we put it into the function. And this might be a little confusing to all of you, but it's actually not that complicated, I guess. So one way to think about it is if I have a candy machine. So my function is actually a candy machine. And the candy machine apparently, it just bought a soda, it takes $5. And then it gives you a soda per $5 you put in. So you can think of your function as the candy machine. So basically, f of $5 equals a little soda. And then f of $4 equals nothing. And then f of $10 equals 2 sodas. So there's no discount for buying in bulk. Okay, so that's basically how you should think of a function. So you put $5, you get a soda out. If I put $10, I get 2 sodas out. If I put in $4, it doesn't give me anything. And then for every dollar amount, there's something different I'm gonna get. It just so happens that if I put $20, it gives me a little chocolate bar. Yeah, it's made by the Belgians, you know, so they like to charge a lot. Yeah, you know, they buy the raw product from Africa or South America for 15 cents. They just like mix it up with a little butter and then sell it for $20. But anyway, in the $5 soda machine outside, that for some reason is sold out. So I had to walk to the next building, by the way. So all of you have a lot of money on you. Yeah, just... Okay, but anyway, so that's basically your function. Now, imagine now what's happening when you do kind of, so this is f of x, but really when you do your convolution, you have to do some operations on this function, and so we have to kind of start to consider, what if now, so that's just a function, but what if now you have your same candy machine, and there is this person here, and then this person here has a little hat, and then he happens to be a felon. And so this felon here basically when you put in $5, into the machine, it actually takes $2, and then it only puts in $3. So it just takes $2 for himself. So if I put $5 here, Felon here will take $2, and then we'll put $3 into the machine. If I put in $6, then he's gonna still take $2, and then now there's gonna be $4. So now what I have here is f of x minus 2. So these are the $2 that, so now what ends up happening is that if I plug in f of $4 minus 2, that's gonna give me 0. Now, if I give the machine $6, I still get nothing. So now I actually have to give it $7 to get my soda. So effectively, this is what happens when you shift the function. So if I were to kind of plot this in the XY, and this is number of sodas, and then this would be 5, 10, 15. I'm not gonna go to 20 because then it becomes chocolate. 1, 2, 3. Then it's just gonna look like, boop, 1, and then 2 sodas, and then 3 sodas. But now if I were to plot for the function kind of at the bottom, since Felon here is taking $2, now it's gonna be 7, 12, 17. Then I'm gonna have 1, 2, and 3 sodas. So kind of everything just shifted by 2 to the right because someone's taking $2 every time I input it into the function. So basically, when you think of these arguments, what you input is the x, there could be some other operations. For example, let's say instead of having a Felon here, let's say you have Santa Claus. And Santa Claus actually gives you $7. So in that case, it would be f plus 7. So if you want a soda, you can just take $2 from Santa Claus. Well, that's his beard. But anyway, so just do realize that if you just think of the function as a candy machine that gives you something every time you input something to it, then you can think of whatever's happening inside these parentheses as something that's happening right before you input your money into your soda machine or whatever. If you understood everything I said here, then convolution shouldn't be that challenging because effectively what we are trying to calculate is okay. What we're trying to calculate here is the integral from negative infinity to infinity of f of tau g sub t minus tau d tau, where f, that would be f of t convolved with g of t. So if f of t looks something like this, so this is f of t, and then let's say g of t looks like this, then g of negative t would look like this, because whenever I put a 1 into this one, it's the equivalent of putting negative 1 here, whenever I put -1 in here, it's the equivalent of putting 1 in here. So it just mirrors around the y-axis. Now, and maybe I should just say this in terms of tau to make this better. So g sub tau, and this is of negative tau. Now, if I take this g sub negative tau and I shift it by t, so I'm gonna add t to it. So I have g's of negative tau plus t. Well, whatever happens if I plug in for tau, t, that should be the same thing that happens at 0 for g. And so let's say t is here, that should be right there. And then if I plug in some value smaller than t, so if tau is smaller than t, then whatever's in the parentheses will be positive. And so it's going to look something like this and then go down, and vice versa. Does this make sense to everyone? So basically, this corresponds to g's of 0. And let's say this is g's of 3. Well, since this is g's of negative tau, this corresponds to g's of 3. And here would be -3. Now, here would be whenever negative tau plus t equals 3. That should occur here, because that's when this argument here coming into g is 3. Yes? No? So just remember, this is your candy machine. And for some reason, this candy machine, tau is what you give the candy machine. So for some reason, this candy machine, if you ask it for a soda, instead of you having to give it $5, it gives you $5. So that's why it's negative in front. But on top of that, there's a felon here that's actually giving you T amounts of dollars. So basically, the soda doesn't cost you $5. The thing gives you $5 for taking the soda, and then there's Santa Claus that gives you T dollars afterwards. And so that's why now, in order to get your soda, you need that negative tau plus T equals 5. This is the dollars that the candy machine is giving you. This is the dollars that the Santa Claus is giving to you, or taking from you, sorry. Yeah. So anyway, that's kind of all. So if you think about this, you just need to make sure that this argument means the conditions. And why do I kind of emphasize this? Okay, well, let's go back to the beginning. So for this class, I went over a lot of things in the previous class, and kind of one of the most important things that I really want you to know when you do convolution is how to deal with this. The integral from negative infinity to infinity, use of t minus 5 convolved with use of t minus 3, which is equal to use of tau minus 5, use of t minus tau minus 3, d tau. So I want you to be able to do something that looks like this, or maybe if I put a t here, or t squared, it doesn't really matter. If you can deal with time-shifted unit step functions, I'm happy. But to do that, you need to kind of understand that, first of all, if you look at the unit step function, use of tau, it's just going to be 0 whenever tau is less than 0, and it's going to be 1 whenever tau is greater than 0. In this particular case, because the argument is tau minus 5, that means that this thing will turn on, or whenever tau minus 5 is less than 0, this thing will be equal use of tau minus 5 will be equal to 0. And whenever tau minus 5 is greater than 0, use of tau minus 5 will be equal to 1. Now, saying that tau minus 5 is less than 0 is the same thing as saying tau is less than 5. And saying that tau minus 5 is greater than 0 is the same thing as saying as tau is greater than 5. That makes sense? Okay, so since we know that this thing is 0 whenever tau is less than 5, what is the value of this integrand when tau is less than 5? 0. So do we really need to do the integral from negative infinity to 5? No, because it's just going to be 0, so we can just replace this limit with a 5. Okay, so that's one thing we can do. So let me erase this. So we can go through the same exact logic here. We look at this argument here, and we know that whenever t minus tau minus 3 is less than 0, then use of t minus tau minus 3 will be equal to 0. But another way to say that is whenever tau is less than t minus 3. So I moved the tau to the other side. So basically I moved the tau to the other side. And then this should be the opposite way. Yeah. Yeah. So saying that t minus tau minus 3 is less than 0 is the same thing as saying that tau is greater than t minus 3. Since we know that whenever tau is greater than 3, the second argument is 0, do we really need to do this integral for time greater than t minus 3? Okay, so then that means that this is just t minus 3. So at that point, I can just rewrite this whole thing. So I have minus 5 t minus 3 tau use of tau minus 5 use of t minus tau minus 3 d tau. Okay, so there's one more thing that we need to kind of make sure. So remember that when we did this integral, if we look at this first function, it's going to be 0 until 5, right? So if this upper limit here that we're integrating, if t minus 3 falls down here, then we're integrating from 5 to t minus 3. So what would be the value of this integral? 0. So whenever this upper limit is greater than is smaller than the lower limit, so whenever t minus 3 or upper limit is less than the lower limit, which in this case is 5, our convolution should be 0. So now we're going to get that this is actually equal to 0 whenever t minus 3 is less than 5. And then whenever t minus 3 is greater than 5, so t minus 3 is greater than 5, then we actually have to do this integral tau d tau from 5 to t minus 3. Does this make sense to everyone? Yes, no, maybe?
I have a question.
Yeah.
So, if you looked at your first integral where you wrote it all out, since u tau minus 5 and u t minus tau minus 3 all are 0, is that why you're left with only tau, like when you evaluate that integral on the right side?
Well, they're both 1, so 1 times 1 is 1. So both of them will be 1 in the range from 5 to t minus 3. So it's really tau times 1 times 1. Now at this point, of course, I hope that all of you can do this integral. So that's just tau squared over tau squared over 2. So you have tau squared over 2 evaluated at 5 and evaluated at t minus 3. And so that's just going to give you basically 0 for t less than 8. And then it's going to give you t minus 3 over 2 squared minus 25 over 2 for t greater than 8. Now, we don't really write this anymore. What we really will write instead is t minus 3 over 2 squared minus 25 over 2, use of t minus 8. And then that use of t minus 8 actually takes care of the fact that this thing has to be 0 whenever t is less than 8. Is this... Who's lost at this point? No one? Okay, so that means we can have the quiz today. Okay, good. All right. Any other questions, concerns about this?
Yeah, I just have one question. See how we build up the, like when you're writing the outer function, can you switch it? Can you put like tau u t minus 3 or u t minus tau minus 5? Is that going to be the same answer?
Yeah, because the convolution is associative. So you could have done the math.
Yeah, but then I switch the limits or how is that?
No, I mean, so, okay. So it turns out, last lecture we showed that this is actually equal to, I could have done it, so this is minus 3, and then there should be a tau here. There should be. This is actually equivalent to me doing this integral from negative infinity to infinity of use of tau minus 3, and then t minus tau, use of t minus tau minus 5 d tau. So I could have basically this convolution is the same as, so basically you have that tau or t use of t minus 5 convolved with use of t minus 3 is equal to use of t minus 3 convolved with t use of t minus 5. So it doesn't really matter whether you replace this one with t minus tau or you replace this one with t minus tau. You just have to pick one for tau and one for t minus tau. It doesn't really matter which one. Questions? Other questions? Okay, so let's get started with lecture since there are no other questions. So we went over switch circuits, and we basically said we would start kind of from initial conditions for time less than some T1. And then using those initial conditions, we would solve the circuit for each DC input in order to get our solution. And then we also said that the initial conditions can only be determined for continuous quantities, which are the capacitor voltage and the inductor current. So you can't really solve for anything. You can't not extract initial conditions from anything else from a circuit. Questions about switch circuits at this point? No questions. We can move on. We went over convolution, and like I just said, it's commutative, meaning that it doesn't matter which one gets the t and which one gets the t minus tau. It's also associative, so you can do it in any order you want. And also it has this kind of a distributive property, so it behaves pretty much like addition or multiplication. And it also has an identity, which is the delta function. So x of t convolved with deltas of t is just x of t. So an important property, so you can basically, this is not that important of a property. I think you might use this in the homework. But an important property is this time shifting property. So basically, if I have e to the negative 3t and I convolve it with deltas of t minus 5, what would be the answer? Or here, let me just make this more complicated. So to do this convolution, whenever you convolve with a time-shifted delta function, you just take every t and replace it by t minus 5. That's it. Here I can put a u of t here if I want to. And that the way that's going to change it is that now this becomes u of t minus 5. So it's important that you know this time-shifting property, which basically says if I have some function of t and I convolve it with a time-shifted delta function, I get the same function back shifted by that delay. And then there was this convolution with the unit step, which is that if you have a function times a unit step, convolved with that unit step, it's the integral from 0 to t of the function times the unit step function. Questions at this point about convolution? No questions, okay. All right, so then we talked about the impulse response, and then we said that if we know the impulse response to a circuit, in order to find, so this is the impulse response. In order to find the output of that circuit, so like this could be a capacitor voltage, we just need to convolve the impulse response with the input voltage or the forcing function. Or not, it could be an input voltage or current, it doesn't really matter. And so basically, that means that for any input, if we have an impulse response, we can find the output by simply convolving it with that impulse response, basically. And then we said that to find the impulse response, what we would do is first find the solution due to a unit step input, and then take the derivative of that solution, and that would give us the impulse response. So if we have the what we call the step response, so if I give you the step response to a circuit, how do you find the impulse response? Yeah? Yeah, you take the derivative of the step response to get the impulse response. Once you have the impulse response, you just need to convolve it with the input in order to get the output. Questions about this? No questions? All right. In the interest of time, I'm going to skip this. It's going to give you an overview of some of the stuff I do in research and how it connects. to what we're learning, but I guess we can talk about this a little bit. So basically, I work in this area called brain stimulation, where you use either a coil or you use electrodes. So I don't know if you've seen One Flew Over a Cuckoo's Nest, where they put the electrodes and they shock the person. That's called brain stimulation, or the modern version of that. And the idea is basically very simple, that you're going to either use a strong magnetic field to push ions out of neurons, thereby causing brain activity. So ions are charged species, and so if you subject them to an electric field, they're going to be subjected to a force, and so you can cause cells to exchange ions through using electric fields, and that's the basic underlying principle. In particular, there's kind of this experiment people do, which is called motor evoked potential, and the idea is very simple. You take the coil, and then you put it like right over the motor cortex, so somewhere like right here, where this is called the hen knob region. So this area of the brain is responsible for hand movement. And then what you do is you induce a strong magnetic pulse, which triggers these neurons there. It activates them. And then there's kind of a synapse, and then the signal travels down your body, eventually reaching your hand, and then basically there's going to be an involuntary finger movement. And then what you do is you record this finger movement, and then people use this to figure out how much amount of current you need to activate the brain. And then when they do depression treatments, they typically define those relative to the amount of current you need to elicit this finger movement. Now, biologically, what's happening, the way we think about this is you have your coil, and then you have your brain. Then what you can do is figure out what electric field you're inducing in different brain regions. And then what you have is an equivalent circuit for your neuron, and then you couple that circuit to that electric field, and then you can predict kind of how much current you need to stimulate that given neuron. Now from this, you can already get some intuition, because as you can see here, the circuit that we're looking at here, that's your model for the neuron, is actually a capacitor in parallel with a bunch of resistances. So it's just an RC circuit. Now, if we were to derive the differential equation for this circuit, it's going to give us that I applied has to be equal to C ddt of Vm, let's say this is Vm, plus the equivalent resistance of this thing, R, and then you have kind of, let's just assume this VNA is 0 and 0, just to simplify things, times Vm. So this is your typical standard RC circuit. Now, different types of cells, we have a different value of R, and they will also have a different voltage that they need to reach in order to be activated. Now, depending on the value of these resistances, that determines how much current you need to actually elicit a response. In addition, how much time you need to keep that on. So remember that our solution for this is going to be e to the negative t over RC. So each cell has a different R associated with it, and so it's going to have a different latency. And typically, kind of depending on the type of cell, it's kind of responds faster than other cells. Anyway, with the stuff that you've learned so far, you can pretty much understand all of this physiological stuff. So that's just kind of to motivate your learning, I guess. I'm supposed to give you real world examples. Yeah, questions up to this point? All right, let's look at some examples, although we're almost out of time. In the interest of time, I am going to skip this because it's not relevant to the quiz. Here, I'm gonna derive the initial conditions for this one, but I'm not gonna solve it. So for time less than 0, you can assume that this source has been on for a very long time. So after a very long time, how does that inductor behave?
Like short.
Yeah. And then the capacitor will behave as an open. And so that means that for time less than 0, there is no current flowing through here, which means that this voltage will be 3 volts. And then this voltage will be 0 volts. So we have that VC equals 3. And then the amount of current flowing through the inductor, IL, will be equal to 0. But you know that IL is also equal to IC, which is C ddt of VC. So the initial conditions you can get from these are the capacitor voltage and its derivative. Does that make sense? You cannot extract the voltage across the resistor. You cannot extract, because that's going to jump immediately after you flip that switch. Okay, let's just keep going. Okay, let's skip the rest. All right, let's look at this example. So let's say I asked you to evaluate this. So first step, from negative infinity to infinity, e to the negative 5 tau, use of tau minus 2, use of t minus tau minus 3, d tau. First step. So remember that use of tau is equal to 0 when tau is less than 0, 1 when tau is greater than 0. So what this means is that use of tau minus 2 is going to be 0 whenever tau minus 2 is less than 0, and 1 whenever tau minus 2 is greater than 0. So how many of you think the lower limit should be 0? 1, 2, 2, okay. Yeah, so it's 2. So since this thing is 0 whenever tau is less than 2, this whole product is going to be 0 for any value less than 2, so I can just replace this lower limit. Here, let me change colors. With a 2. Okay. Now let's look at this argument here. So again, now we're going to have use of t minus tau minus 3, 0 whenever t minus tau minus 3 is less than 0, 1 whenever t minus tau minus 3 is greater than 0. I can move the tau to the other side so that now it's 0, 1. Whoa. Hello. Whenever t. No, we haven't started.
You say what?
Oh, quiz is in 10 minutes.
Oh, okay, okay, that's fine.
This guy. What? Dios. Okay. I lost my train of thought. T minus 3 less than tau. So I just moved the tau to the other side. T minus 3 greater than tau. Okay, so this basically says that whenever tau is bigger than t minus 3, this thing will be 0. So 0 times anything is going to give us 0. So what should be my upper limit? T minus 1? T minus 2? Yeah, t minus 3. Now, note that if t minus 3 is less than 2, remember, this thing will be always 0 for any value less than 2. So that means that now we have two situations. We're going to have that this is equal to 0 whenever the upper limit is less than the lower limit. And then otherwise, so t minus 3 greater than 2, it's just going to be the integral of -5 tau d tau from 2 to t minus 3. And then at this point, are there any questions at this point? Okay, now I can rewrite this in shorthand as I can move this to the other side. So I'm going to have t less than 5, t greater than 5. I can just rewrite this whole thing as use of t minus 5, the integral from 2 to t minus 3, e to the -5 tau d tau, and that's just equal to e to the -5 tau over -5 to t minus 3. Then you have to evaluate that. Oh, and then I have to multiply this by use of t minus 5. Did I lose anyone? No?
So in the exam, I only need to write the last step, right? I don't need to write the piece of 0.
The exam, you just need to get the right answer, but it's the but yeah, so you just need to write this. Yeah, I mean, you can go directly. I'm trying to go through the whole logic so that we're clear that I'm not like just doing magic here. Is this kind of clear to everyone? If you can do a convolution like this, and you can do a convolution like this, convolved with here, e to the -2t. I'm not going to ask you anything that's not some variation on this, basically, in terms of convolution. If you can do those two things, for me, that's victory. Because next class, you're going to be doing a lot of convolutions, and so you can build upon this little bit of knowledge. I think this will actually put you at a good place for the next class. Oh yeah, so what's this convolution? Can anyone tell me what I have to do to all of the t's? Yeah, so this is just e to the -2, t minus 3, t minus 3. Just remember always to put the t minus 3's in parentheses because it's the answer is actually e to the -2t plus 6. Because you have to, so make sure that whenever you do any kind of replacement, you just put it in parentheses. Same thing when you apply this t minus tau, just put the t minus tau in parentheses, you'll be fine. T minus 3, okay. So that's convolution. Let's forget about this. So how do we find the unit step response for this circuit? What do we assume Vn is? Well, we assume it's a unit step function, so we basically assume that it's going to be 1 for t greater than 0, 0 otherwise. So we get that VCs of 0. So whenever we find the unit step response, remember the initial conditions will always be 0, because we assume that the circuit has been connected to no source for all time less than 0. And then for time greater than 0, we're going to have that 1 equals R times C ddt Vc. So this is the current going through the resistor plus the voltage across the capacitor. So first we have to find the particular solution, which in this case, if you take the time derivative of 1, that's just going to be 0. So we're going to get that Vc particular is just 1. And then we have to find Vc homogeneous. So first we say 0 equals RC lambda plus 1, which gives us that lambda equals negative 1 over RC. And then we can use our initial condition to find the total solution. So basically we have Vc's of t equals 1 plus C homogeneous e to the negative t over RC. And then Vc's of 0 will be just 1 plus C homogeneous times e to the 0, which is just 1. So that gives us that C homogeneous equals negative 1. And so now we have the step response. So here's the step response we got from the from this circuit. Okay, once we know the step response, how do we get the impulse response? Okay, so if I give you the step response, what do you do to it to get the impulse response? Take the derivative. Okay. He's like, well, if he ignored me last time, I might as well say the next time. Okay, so you take the derivative of this. So I'm going to take the derivative. So it's going to be d dt of 1 minus e to the negative t over RC times u of t plus 1 minus e to the negative t over RC ddt of u of t. Now this is just the delta function by definition. But remember, the delta function is only non-zero at 0. So it doesn't matter. We can replace whatever multiplies this with whatever we want for any value less than 0. So we can just plug in for t equals 0 here. And so we're actually going to get that this is just 0 times the delta function, which is just equal to 0. And then now we need to take this derivative here. The derivative of 1 is just 0. The derivative of negative t over RC is just negative 1 over RC times e to the negative t. So we're going to get that this is just equal to use of t e to the negative t over RC. Over RC. And there should be, yeah, perfect. Questions at this point? Does everyone understand why this term is 0? Okay. All right, so once you know the input response, you can basically use it to find the output to any input. by simply convolving it to that input. And we already went over convolution, so we can get started with our quiz.
Like reverse hump them.
What happened?
Who invented this so I can reverse hump them? Yeah, you gotta summon them and then you make fun of them. No, this is it. It's no joke from here.
Dude, if this is what Lisa breaks this major for you, I got bad news.
I don't know.